and thank you all for doing the effort to come over and have a flavor of one of the mega projects. Thank you, Shishir, for forming the basis for this talk. Uh, a friend of mine who is 20 years, I think we are friends for 20 years, and he's sitting in the audience. As soon as he walked in, the first question he asked is, "क्या भाई अभी भी 50 साल दूर है?" So I think Shishir made you realize the magnanimity of this project and the complexity of this project. And as I go through my slides, I will make you, or maybe you'll appreciate it more from the sizes that we have to handle and the processes we have to go through. Uh, this talk essentially covers our footsteps that we evolved and that we follow to ensure that the India's commitments are delivered to ITER at the right time, of the right quality, and of the right magnitude. So this is an overview talk. I tell you about all the 9 packages that we are delivering to ITER, and so this talk is on behalf of the various members of the ITER India team. This is not much is my work. It's a team effort which is being put in to ensure the deliveries. So with this brief introduction, I just go to the first slide, which is what will you see if you peep inside ITER machine. So if you peep inside an ITER machine, you will see various components. The first one would be the Cryostat. Then we have thermal shields. We have a vacuum vessel. We have the poloidal and the toroidal field coils, and many more systems. And each of these systems are in-kind contributions made by different countries. In some cases, a single country delivers the in-kind contribution. In other cases, it is a group of countries which are delivering a certain component. So that is why we say that each component of the machine is an in-kind deliverable, either by a single ITER partner. The flags of all the ITER partners are flying high, as you see on the top of the slide, and or they are delivered by multiple ITER partners. This is just to give you a brief overview of how the system is working. And now I come particularly to the packages from India. The packages from India are Cryostat, which is basically a jacket for the machine to ensure an ultra cool vacuum environment. I will go into the details of these packages as I go slide by slide, but this is just an introduction. The second package is the in-wall shields. The in-wall shields their function is to perform the neutron shielding basically, and also to help the magnetic field ripple changes to not reach inside and thus help in better control of the plasma. The in-wall shields are placed between the double walls of the vacuum vessel for the ITER. Then we have the cooling water systems. Now, cooling water system is an example where there are multiple partners, and India is one of them. So we have a certain part of the supply for the entire cooling water system. Similarly, is the cryogenic system, where some parts of the system, like the magnets or the cryopumps, had to be cooled to sub-zero temperatures. Then, obviously, we have to heat the plasma. So the heating is done in 2 ways. One is the beam heating, and the other is the RF heating. The RF heating takes the ion cyclotron resonance heating and the electron cyclotron resonance heating. There is a beam heating as well, but that is not part of India's delivery to ITER, so I haven't listed here, but it will be a mention in my talk later. What we supply in terms of beams is a diagnostic neutral beam, whose function is basically to diagnose the helium ash content in the plasma when the DT reaction takes place. Then, obviously, to run these systems, we need a lot of power supplies. So, power supply systems for the heating and heating and the diagnostic neutral beam are a part of this package. And finally, we have some contributions to the diagnostics as well. So these are the 9 packages which India signed up for when we joined ITER. And now, once we had made this commitment, so we wanted to develop a roadmap. Roadmap is basically was to ensure that we deliver the packages, and for delivering them, what do we have to do? So basically, what footsteps we have to create and follow to deliver those packages. So what we thought was that definitely we need a R&D program for relevant areas of fusion technology. Then we need to interact with a lot of academia and Indian industry to help develop this R&D, because we were very sure that there are pockets in all major institutes and centers for excellence whose knowledge or whose experience can definitely be utilized in one way or the other to ensure the delivery of the packages. Then we have to also concentrate on the areas of quality development and documentation. This is one area which is normally not practiced by the students or the people working in the lab. We do not ever create proper documentation, or do not, in many cases, care for the kind of quality that we look for. But these are essentials for a large supply like ITER. So we had to focus this on these areas specifically. Then we had to develop most of the components we wanted to develop with the Indian industry in order to help Indian industry come into state of readiness when we reach a stage where we want to make a reactor for ourselves. So we have to work with Indian industry to develop the state-of-art facilities. And then the developed products which we have after a certain time, of course they have to be certified for their performance in many cases. So we have to have different areas of our test beds which is being done in the ITER India lab at IPR. And then follow up. There are cases where today the technology does not exist in the country, but we need to develop those technologies if we want to have a technology readiness in terms of the entire machine. There are some industries which do a certain job, and there is only one industry which does worldwide. So what we thought was, okay, let us work with them, but in parallel develop our own Indian industry, learning from the experiences of foreign industry, and take a path of parallel development, so that we, after some efforts and some time, we are able to produce products which will be of use for us later. So this is the kind of India's roadmap towards the delivery of the components. And then I come to the first package. The first package is a Cryostat. As I said, it's just a jacket which is to ensure an ultra cool environment and in the machine. Now the thing is that this monster is 30 meters high and 30 meters wide. I mean, when we are students working as experimentalists in labs, we never imagine such kind of dimensions for our components. In fact, when we were at Nuclear Science Center, the HERA, the heavy ion reaction analyzer, was like a mega project for us, because it was really mega at that point of time. But when I saw with my eyes the dimensions of these components, I really thought we are on a mega journey. And this monster requires 3,800 tons of steel to build. It's one of the largest stainless steel vacuum vessel which is being built, and has a volume of 16,000 meter cube. And of course, it has to be evacuated, so it should have a vacuum of 10 to the minus 6 torr. Then we move on to the second component. As I said, was the in-wall shield blocks. They are for shielding the neutron radiation for components situated outside the vacuum vessel, because this is a nuclear site and we have to follow the French rules of safety and regulations. And that is why it is very necessary to ensure that that our radiations are not very high. So the shield blocks are for that. And as I had said earlier, that they limit the perturbations due to toroidal field ripple, and thus help in plasma performance. They occupy about 55% of the space between two walls of the vacuum vessel. It's a structure of 8,000 blocks of different shapes and sizes, and these blocks have 72,000 plates. And these plates are made of borated steel and ferritic steel plates, for the reasons that are of safety and preventing the toroidal field ripples to create the plasma disturbances. So this is an example of in-wall shield blocks that we have to supply. Then the next package comes in is the water cooling of the heated components. As you see, it's a massive structure in terms of pipelines, in terms of the paraphernalia or the auxiliaries which are required for maintaining a certain water quality at a certain pressure drop, at a certain flow, and all other related parameters. So, and this water is used to remove heat from the vacuum vessel and its components, and it is also used to cool auxiliary systems such as the RF and the beam heating and current drive systems. Even the chilled water system is required for the cryogenic system, and then the power supplies and the distribution systems also have to be cooled. So this is their basic function. And to ensure this basic function, there are multiple loops, as you can imagine from the figure you see on the right. So there are multiple closed heat transfer loops. And finally, there's an open loop as well, which is called the heat rejection system. Then, how do these loop function? You start with the heat generating during operation, which is transferred to the tokamak cooling water system, which we call as TCWS. Then we go to an intermediate component cooling water systems, and finally to the heat rejection system, where we reject the heat to the environment. Now, where does India come in here? India comes in three systems. One is the component cooling water system. This is the cooling water system which supplies water to the various components at 31 degrees centigrade. It has a specified flow rate and pressure and water quality. We also provide systems for the chilled water system, which is at 6 degrees centigrade at a specified flow rate and pressure. And then even in the final heat sink, we have a contribution. What do these contributions consist of? They consist of 10 cells of cooling power, and the cooling tower should have the capability of an average of 510 megawatts and a peak 1.2 gigawatt. We have plate type heat exchangers, each having a capability of 70 megawatts, and possibly this is at the highest range of design. And 6 air chilled coolers, which is 450 kilowatt each, with the requirement of 6 seismic qualification for nuclear site. Now, this is another thing which is the first of its kind, but it's important from the ITER's operation point of view. And it also includes a lot of pipes. So there are about 4,500 spools of pipes ranging from diameters of 20 millimeters to 2 meters and of varying lengths and geometries. In total, we have a 20 kilometer of piping, and if we add up all the welding lengths, we have 100. They're equivalent to about 105-inch diameter of welding. The third system is the cryo cooling system, or the cryo distribution system. This one is also as complex as the cooling water system, as I said, and its main function is to support the cryolines, and the cryo distribution system support the liquid helium and liquid nitrogen plant facilities at ITER. The liquid helium plant facility is a 75 kilowatt at 4.5 Kelvin, and the liquid nitrogen facility is a 80 kilowatt at 1 megawatt. 80 Kelvin, 1 megawatt. So, as it was said during the inauguration session, that this is one of the largest cryo system on a single platform, which is available worldwide. Though LHC also has a number of cryo plant systems, but in terms of size of a single sub plant, this is one of the largest. And these are used to cool the ITER magnets using superconducting coils. They are also used for forced flow of helium at 80 K for the cryostat and thermal shields. And then you have cryosorption pumps, which are located at different positions in the machine to ensure the right kind of a vacuum environment. And you utilize these cryogens to keep the pumps going and hence maintain the desired vacuum. What does the Indian scope include? It includes 4 kilometers of long cryo lines, 7 kilometers long warm lines, and 7 cryo distribution boxes, which are just like storage houses. So which are just like local storage houses. Moving on to the next system, which is the energetic neutral beams into the plasma. As I said in the beginning of my talk, there are beams which are required to raise the plasma temperature, also act as a current drive. But these beams are at 1 megavolt, and they are 40 amperes of B minus beams, or 870 kV 46 amps H minus beams. Now look at the currents, 40 amps, 46 amps. The energies, okay, I mean, if you start comparing with the Pelletron accelerator, okay, you will say we have higher energies. But if you look at the current, the Pelletrons operate at milliamps or microamps of currents, whereas here the currents are amps. So now this system of heating and current drive is actually being supplied by EU and Japan. But a similar system, what we have is the diagnostic neutral beam, where we are lower in the energy, it's only 100 kV, but higher in the current. We have to produce about 60 amps of H minus beams to meet the requirements of a neutral beam of 20 amperes going into the plasma. Now the system is massive. If you look at it, you have a vacuum vessel which houses an RF based ion source which looks like this. I will come into more details later. Then this is used to produce this 100 kV 60 amp H minus beam. it has three grids. It has a three-grid system, which unfortunately is the only optics controlling element for the whole transport path. We do not have quadrupole magnets or sextupole magnets or shaping devices to control the beam as it moves forward, as it happens in the accelerator. The physics design of this, therefore, the physics design of this accelerator, sorry, therefore the physics design of this accelerator becomes very important. We produce these beams, but we want neutrals. So how do we neutralize them? So we have a neutralizing cell here. This one, this is the neutralizer cell. We flow hydrogen gas into the system, and the H minus beam interact with hydrogen, and at these energies the efficiency of conversion is 60%, which means for every 100 ions going into the system we'll have only 60 neutrals. We still have 40 ions which are coming out, and we need to get rid of these ions. So the next device which follows is an electrostatic residual ion dump. This is a set of parallel plates. We apply electric fields and deflect the positive and negative ions out of the beam. And finally, we have another device which is called the calorimeter, which is actually a diagnosis for the beam. So this is the device. It consists of two arms which can open and close. The beam falls on that, and doing water calorimetry, we establish the profile of the beam. And once we have satisfied with the quality of the beam, then we open up the arms of this calorimeter, and the beam moves further 11 meters down where it starts injecting into the plasma. So this is the basic function of a neutral beam injector. So this was a small movie, but just to illustrate what I said in a different way. We start with, as I said, we have an ion source, which is the RF-based ion source. We have an RF generator. Inductively couple the power. We have a plasma. Then we go into a board which is called the surface board, where we inject cesium into the source, and we are able to get current densities of the order of 35 milliamps per centimeter square. Now, since we are extracting negative ions from the source, we all obviously would extract electrons as well. These electrons are unwanted species for us, and we should dump them somewhere. So we have magnets placed in the second grid of this accelerator system, where the electrons are deflected and dumped onto this grid, and the negative ions move forward. Then here is the hydrogen ions, which is interacting with these hydrogen atoms, which are interacting with this ion beam, and you have a conversion of 56% neutrals, 22% positive ions, and 22% negative ions. You move into the electrostatic RID, you deflect the positive and the negative ions. You have the neutral beam going forward, which is diagnosed on this calorimeter, and once optimized, it goes as neutrals through the duct connecting into the machine. So this is the basic principle to help you visualize how these neutral injectors work. And I move on to the next system with this, which is the RF plasma heating systems in tokamaks. They are required for the startup, for heating and current drive as well, like the beams, and they are also used for wall conditioning and to control ELMs, which are basically edge localized modes which can disrupt the plasma. Now, there are two types of systems. One is the ion cyclotron resonance heating system, where we have 9 RF sources. This is the 2.5 megawatts 2.5 megawatts at a frequency of 35 to 65 megahertz. And then we have the electron cyclotron heating systems, which are gyrotrons. Out of the 24 that are required for the machine, India is supposed to supply 2 of them, and each of these is rated for 1 megawatt at 170 gigahertz. So these are the RF systems which we have to supply, and then comes the power supplies. As I said, for the diagnostic neutral beam, we'll have an extraction power supply, which is 10 kilovolt and 140 amps. So 1.4 megawatts. Acceleration power supply, 90 kilovolt and 70 amps, because you are accelerating up to 60 amps of beam, and you may have some electrons somewhere. So you have to have that capability. In addition, for producing the plasma, you have to have RF generators. There are 4 of these, each at 1 megahertz and 200 kilowatts of power. And then you have to have an electrostatic residual ion dump power supply, which is for separating the positive and negative ions from the neutral beam. And this is a 8 kilovolt, 60 amps power supply. Similarly, for the RF system, we have ICRH. For the ICRH, we have power supplies. One is the driver stage and the other is the end stage, with the specifications shown there. And similarly for ECRH, we have a 55 kilovolt, 5.5 megawatt power supply. Now, we move on to the diagnostics, which is the last package. We have X-ray crystal spectroscopy. We have electron cyclotron emission. We have charge exchange resonance spectroscopy, which is basically derived or done with the help of the 100 kV 60 amp H minus beams, or the neutral beams which we are injecting into the plasma from the diagnostic neutral beam injector. And then we have an upper port where there are a lot of integration and interspace issues to be solved, in addition to the CXRS being done at the edge of the plasma. So this is the diagnostics package. Now let us go to the components, how we went around making those components. So when we looked at what kind of ITER components do we have to supply, there are requirements. What are their requirements? Their requirements are that we have to adhere to certain norms which are related to vacuum, quality, safety, seismic adaptability, remote handling, and even the codes like the ESPN code, the pressure equipment directives, and tritium classification, etc. And all these requirements actually form the basis of the design of the component, the materials required for the component, the fabrication, the testing, and repair. The most important thing here is that once it goes into nuclear state, which is the DT, after we start the DT operation in the machine, the components should survive the lifetime of ITER, because the remote handling, because going and repair is difficult, it can only be done by remote handling means. Just to give you an example of how the classification is done, I have taken one example, which is related to the vacuum classifications. We call them as vacuum quality class 1, 2, 3, and 4. The X refers to which component are we talking about in the whole machine, and then X has a further qualification of A and B, where we say that this component forms the primary vacuum boundary, for example, a vacuum vessel, or if the component is sitting inside a vacuum vessel, it doesn't form a primary vacuum boundary. So these are some classifications which we always have to keep into account when we go about thinking about the systems we have to manufacture and deliver. Now, since I see some students here, I go through the basic steps just to make them realize the magnanimity of this whole exercise. So for realizing any ITER component, the first thing which we have to do is the physics design calculation. Once we are satisfied with it and we establish what we want, then we have to engineer the component accordingly. After the engineering, we go into manufacturing, but manufacturing involves a lot of stages. It involves also a lot of prototyping, because many of these components are first of their kinds. I will go into a bit detail in the next following slides. Then once it's manufactured, we test it and we do experiments to optimize its performance, and finally we have the deliverable ready. Now I go to specifics. Let's go to the engineering of a component. The engineering of a component starts with, after we have done the physics calculations, we say, okay, how should the component look like? Where all the component has to sit in the machine? What are the surrounding interfaces it has adapted to? What are its functional specifications? Basically, if we take a power supply, then what current, what voltage, or if we take a component, let us say an ion source, then it has to deliver this much of current, or if we take a source, RF source, then what is the power it has to deliver, and things like that. So those are the functional specifications for the system. And also, most important is the safety requirements, which have to conform to the standards I mentioned above. Then this next step is, what are the loads that this component is going to see in terms of thermal loads, because of the power deposition on various components, in terms of the electromagnetic loads, because the components are working in the machine, then the seismic loads, because seismic events can happen. Fukushima was a good example of that. The nuclear loads, the cyclic load, and whether the loads are cyclic or continuous. So this is the kind of matrix we have to make for the load analysis. And once you have done that, you go to the next step, which is engineering calculations. What you do is you take the component, you apply the loads, do some kind of an analysis, and find out what would be the deflections, deformations, cooling requirements, etc., to ensure that the system works as per what is required. Once you are finished with that, the next step is benchmarking those calculations, because you have to show to ITER that these numbers that you have got out of these engineering calculations conform to certain codes which are specified by ITER, and they also conform to the French safety regulations, again because of the site being in ITER. Then you have benchmarked, and then comes the next step, which is the tolerance for the manufacturing. because each component is an assembly of a large number of subcomponents. So you have to worry about tolerances on the subcomponent level to ensure that when you assemble all those subcomponents, you get a component which ensures the tolerances that you are looking for. And finally, you have a frozen engineering design. From this engineering, you go on to the readiness for manufacture and then go into the manufacturing mode. So manufacturing mode involves, the first step is, okay, what are the materials I'm going to use for this machine? The materials, sometimes they are readily available. In many cases, they are not available. And then we have to decide on the R&D path one has to take. And I will give you examples where this was done. Then the next step is the machining requirements. Basically, deciding what process parameters do I have to use to ensure that the component complies with my requirements. And also look into the jointing requirements, because whenever you have to flow water or a cryogen into the system, you have to transit somewhere from the SS pipes which are carrying the fluid to the material that the component is made of. Then you have to have quality requirements which conform to the standards. You have to have industry identification based on the capabilities, or which industry, even if they do not have the capabilities today, if we help them grow, they will do the entire job and develop their capabilities themselves. Then, as I said, prototype development, where the most important stuff comes, is what is the scale of prototype which we choose, because the whole idea behind doing a prototype is that we make a small component and we establish the procedures, we establish the parameters of manufacturing, and then these parameters should be scalable when we go to the full scale model. In some cases they are not, and for those cases we even have gone for 1:1 prototype. The manufacturing of the actual product takes place, and finally we do a lot of testing which are done at the factory and finally at the site, and we say we are ready with the component. But as you would have heard in Shish's talk, these engineering efforts are of two types. One type is called a build to print design, where the design is ITERs. Why is it ITERs? Because many of the components, as I said, are built for the first time. The design as such is supported by single or a large number of participating countries, but ITER takes the responsibility that, okay, in case this design does not work at a later date, we will provide you with the cost, whatever additional cost is required to develop the component, and we will be responsible for the schedule as well. So these are called the build to print packages. And the next kind of package is a functional specification package. These are packages where similar systems have been built elsewhere, and the route of manufacturing and the confidence in their performance is established. So they say, okay, we want a power supply, let us say, for this and this specifications, and you develop it the way you like it. You choose your topology, you choose your this thing, but all you have to ensure is that at the end it should function the way we want it to function, and any modifications which are required out of that country's effort are at the cost of the partner, and also on the schedule is the partner's responsibility. So if I try to summarize on what of some of the previous slides that I have said, I would say that the partner for either of the engineering approaches mentioned is responsible for the successful delivery and manufacturing of the package to the ITER. Built for the first time, estimates of schedule and cost can go haywire. There are stringent quality requirements. We have to follow French safety rules and regulations, and most important, the components have to survive the lifetime of ITER. So the manufacturing of most of the components, as you would have gathered from Shish's talk, is underway. Uh, so what have we learned? We have learned various areas of engineering. We have learned few things about materials. We have learned about heavy and precision engineering, the jointing of similar and dissimilar materials. We have learned multi-ampere megawatt beam technologies, RF technologies, electrical engineering, cryogenic engineering, hydraulics, diagnostics development, prototype development, how to ensure quality requirements, what kind of documentation we require, and what are the performance tests we have to perform. I will take each of these areas and give you some examples to illustrate what I mean to say. So let us take the area of materials. So as I said, ITER components, some of them are made of special materials. They have to be high strength because there are a lot of power. There's a lot of power which is incident on these materials. They have to be corrosion resistant because they have to last the lifetime of ITER, and most of them are cooled components. And they have to maintain themselves under unique operational conditions, meaning by their mechanical strengths or characteristics should not change under the operational conditions of ITER. Then, obviously, comes the compliance with the nuclear safety requirements. And here are a few examples. The first example is that of a cryostat. Here, the maintenance of the inventory, nuclear inventory, is very important. And as the model of ITER developed, as the nuclear calculations for those models developed, there was a continuous change in the, for example, if we take steel, there was a continuous change in the component of cobalt that should be in the steel, because the nuclear inventory cannot exceed a certain number as per the French regulations. So finally, for the cryostat, we have a cobalt content of 0.1%, which has been made by Jindal Steel, and cryostat is being made out of that. The second example, as I said, is for the package of neutron shields, where we have made borated as well as ferritic steel, which is corrosion resistant, and it has been tested, and now these blocks are being made. The third example is the development of a special material, which is called the copper chromium zirconium material. This material has been made in India in collaboration with NFTDC of Hyderabad. Dr. Balasubramaniam, most of you must be knowing, has been quite helpful in helping us develop this. The most important thing is the control of the materials other than copper into the system, so that it maintains its mechanical strength even at higher temperatures of operation, but it does not increase the nuclear inventory when it comes to radiation. So these are examples of some of the materials which have been made. Coming to heavy and precision engineering, Cryostat, as I said, is a monster of 30 meters wide and 30 meters high. It has been divided into 4 sections: the base, the lower cylinder, upper cylinder, and top lid. But each of these sections is still very big. So we had to decide, it has to be looked as to what machine size can the machines handle while the component is being built. What are the machining tolerances required? How do we ensure the portability of the built up components? And how do we ensure the assembly to the tolerances that we require? Based on these questions, we went in for a segmented approach where the special handling of large pieces up to 100 ton was ensured. And what we also ensured was that the segments were made in such a way that if they were welded together to make the single piece that we require, that dimensionally they are not off by more than 0.3% of the total dimension. Then we have to develop special welding techniques, of course, for this, develop special jigs and fixtures, and finally we have to have a lot of flatness control. So you see the complexity of this whole exercise, which is both heavy because of the size and weight, and also precision because we have to meet the tolerances. These are some pictures of the cryostat under fabrication. So this cryostat is made with a profile like this, and several such profiles are made, are then joined together to get the base of the system. And the profile is obtained, even for this 30-meter diameter, this is obtained within 90 millimeters. Then, if we look at today's status of the cryostat, we have finished the base, we have finished the first, and we are on the second one. So the blue ones are referring to the fabrication completed, and the green ones are referring to the ongoing upper cylinder, which is being fabricated now and is nearing completion. Now these are the segments related to this picture that have been manufactured. These segments are manufactured in India, and then they are ported to France. In France, there is another facility, cryostat assembly facility, which is India's facility in ITER. And here, a lot of mechanics and engineers work together to put these components together as per the desired tolerances. And this is one picture which illustrates this assembly underway. Coming to diagnostic neutral beam, as I said, is another complex system which involves a lot of heavy engineering and precision machining. Heavy engineering, this is for, let us say, a vacuum vessel. Now this vacuum vessel is 10 meters long and 4.5 meters diameter. It's a huge vacuum vessel which will house the ion source, then the neutralizer, the electrostatic RID, and the calorimeter. This is the ion source frame. This is the neutralizer, the electrostatic RID, and the calorimeter frame is there. This is a vessel which has been made in India by an Indian company, and it is installed right now in the Indian test facility at ITER. But the thing is that over this 10-meter long vessel, you have to ensure that you have enough space open for the components to be put in, and once the components are put in, this, if you close the lid, it should give you the vacuum which is required for the operation of the beams. So this is one example of heavy engineering. And coming to precision engineering, for the diagnostic neutral beam, as I said, electrostatic accelerator, extractor and accelerator system is the system which is controlling the optics for the entire 21 meter of path length. So a lot of optics design is first of all done, and then that optics design has to be converted into reality. Now what do we want? We want a 60 amps beam, which basically translates into 35 milliamps per centimeter square of extraction current density, and we have a set of 1280 apertures, and we have 1280 beamlets which are extracted from the source. And if you add this current density and this extraction area, you get a current of 60 amps. But these have to be shaped to determine to get the best of beam optics, minimally diverging beams. And then also you have to focus these beams at a distance of 21 meters. So what you have to do, you have to ensure horizontal focusing and vertical focusing. Now imagine a segment. This one is 1/4 of this total thing that I am showing, but this segment is 800 millimeters wide, 80 centimeters wide, and 440 centimeters high. And we shape each of these 320 apertures in such a way that we get a final focusing at this angle. So we have not only to make these apertures to the desired shapes, but we have also to ensure that there is angling of each of these group of apertures so that we land up with focused beams. That is why if we have to meet the requirement of transport of desired amount of current, we have to ensure that the position accuracy of 50 microns between the three for all the apertures on the grids. We have to ensure the grid has a flatness of 40 microns, and we have to ensure an angle accuracy of 0.01 degrees only. Mind you, these angles are very small. They are only 0.222 degrees and 0.6 degrees. So these are the kind of precision things which come in when you go for specially designed materials or specially designed technologies like the beam technologies. From there, I move on to the joining of materials. The technologies here have to be developed for similar materials and dissimilar materials. I will come to examples of this. Again, one has to move away sometimes from the conventional welding techniques in order to keep the radioactive inventory under control and to meet the safety requirements. The safety requirements also require that the weld joint should be such that they are fully penetrated welds, not on the surface only, and you should be able to inspect each weld. Sometimes the geometries are such that inspection of these welds becomes a difficult criteria. So you have to design your systems keeping all this into account, and various welding techniques which are being used for different components of the machine. There are two specific examples. One is an example of joining two sheets of different thicknesses, which is for the cryostat. You have a 190 millimeters thick sheet, you have a 105 millimeters thick sheet, and you have to weld it across. I mean, okay, if you imagine it, the heat going into each of these would be different, as a result of which the expansion would be different. So you have to have a control on the welding rate. You have to have a control on the jigs and fixtures in such a way that you achieve the tolerances related to the flatness, which is 12 millimeters, and we actually could manage 7 millimeters on this part. The second comes in when, let us say, for example, on the grid systems. So this is a grid, but there are two joints. One is a copper to copper joint, which is done by electron beam welding. Electron beam welding is a localized deposition of power by a very powerful electron beam and through a machine which is used for them. But then we also have to transit from a copper to a stainless steel in order to make the connection to the water distribution system. And this is where a nickel interface comes in, and the whole process parameter for this kind of a dissimilar metal welding had to be developed while we were developing this technology. Now let us come to the cryo lines. The requirements are that for the 4.5K lines, the heat in leaks should not exceed 1.2 watts per meter. And for the 80K lines, the heat in leaks should not exceed more than 4.2 watts per meter. Of course, this is, we in India, while we were doing SST also, had developed these transfer lines with multi-layer insulation. but they were single transfer lines. Here the requirement is that you have to have an assembly of transfer lines which are which look like this, assembly of transfer lines in a single jacket. And this is a technology which we decided to have two companies in it. One was Inox, which was developing this technology, and the other was Air Liquid, which already had this technology. So while some of the complex cryo lines were done by the Air Liquid company, slowly this technology has gotten transferred to Inox, which is an Indian company, and now we have the state of the art facilities at Inox itself to manufacture such kind of complex cryo lines. Uh, what did we additionally gain from this parallel approach is that we could mitigate the risk, we could develop the industry, we could performance test and compare the products coming out from the two industry, and we have finally landed up with an Indian industry which has the capability of doing this. Uh, so till now, total length of 5 kilometers has been manufactured. Diameter of outer vacuum jacket is about 1000 mm, and we use about 7 process pipes in a single cryo line, which is a technology which has been developed. Coming to cryo distribution systems, we have the 5 auxiliary cold boxes, cryo plant termination cold box, and other systems. For the auxiliary cold boxes, we need to develop cold circulators. The cold circulators have to have an efficiency greater than 70%. At 3 kilograms per second and at 4.3 K, the pressure head should not exceed zero point 0.5 bars. So the development of cold circulators in itself has been done for the first time, but it has been done with two companies, IHI and BNI, which are abroad. But parallelly, we are working on developing similar kind of cold circulators in India as well. And finally, these cold circulators have been tested in a 4.5 K class cryogenic test facility at Japan, which is a 5 kilowatt test facility. This test facility is required for testing of such kind of cold circulators, and we do not have a 5 kilowatt facility in India. That is why we had to go to Japan. And this is a picture of the component being tested. Then comes, just to show you a few pictures of the manufactured cryo lines or the cold box which is getting ready for getting transported, the cryo facility which is coming up at the ITER site, and installation of cryo lines at the ITER site. Then we go to the cooling water. As I told you about the requirements, we have made chillers which are 450 kilowatt each, and they also had this requirement of seismic qualification. Basically, what it means is that even if a seismic event occurs, there are some components which have to keep working, and so they should not be disturbed by seismic events. So this is one such component. Then we have to ensure the water quality, which basically means that we have to make a chemical dosing system to ensure the kind of water quality that is delivered to the different components of ITER. And this is showing the 2,500 spools which have been delivered to ITER of different shapes, of different diameters, and would be assembled in future at the ITER site. Coming to electrical engineering, we have made power supplies. For example, for the extraction and the acceleration power supply, this is one example of the acceleration power supply. One of these power supplies has been supplied to RFX Padova, which is developing a test bed for testing an 8-driver source for ITER. This is a picture from there. And similarly, for the ICRF power supplies, we have manufactured the driver stage and end stage power supplies, which have been designed and successfully tested, and they exceed ITER specifications. So then you need some transmission lines to transfer such kind of power over long distances. This kind of a transmission line, it is very complex. It carries electrical lines, it carries hydraulic lines, it carries gas lines, it carries RF lines, all of them in a single enclosure. So this is an example of a transmission line which has been developed at Indian Test Facility in IPR and would be used with the diagnostic beam prototype facility which is coming up. Then RF technologies, of course, when we started, there is no source which can deliver you 2.5 megawatt with a VSWR of 2:1 and at the frequencies and is continuous. So we had to start with developing a source which can deliver powers of 1.5 megawatt, and then we combine two of these sources to get the delivered power of 3 megawatt or 2.5 megawatt at whatever specifications are mentioned above. Now we took an approach of developing two parallel technologies. One is the dicro technology, other is the tetro technology. Under matched loads at different frequencies, this is the graph which shows you that. at different frequencies, it gives a power of 1.5 megawatt in the y-axis for the kind of input power that you want. And the bottom tables show that even at different phase angles, when you are not phase matched, you have output power of 1.5 megawatt from either of these two technologies. Now the next game is to combine two of these to deliver the kind of 3 megawatt that we are looking for. And ITER India has proposed a layout which consists of two parallel 3-stage amplifier chains plus a combiner circuit for doing this. So obviously you would have realized by now how complex these technologies are. No matter how much care we take, do we always get what we want? The answer is no. There are a lot of non-conformities. We may have done a lot of prototyping, we may have developed 1:1 models, we may have done a lot of things. But at the end of the day, because of human errors, because of machine not functioning properly, because of some conditions not being right, we always end up with non-conformities. So the idea is to determine what the non-conformity is, why it happened, can it be avoided, or it is a part of machining limitation. And if it is a part of machining limitation, then we have to go to ITER and say, okay, this is the deviation request we have to file for this kind of a non-conformity, and also prove that even if it exists, it does not affect the functionality of the component. So we do not always get what we want. We have to go through this process also. And then comes the area of prototype development. As I said, the scales have to be chosen very carefully, but it helps you develop technologies and realize the product. Here is an example of various types of prototypes which have been developed for the diagnostic neutral beam, and another set of prototypes where we had to do the sector development for the cryostat. Now this is a very good example where we initially thought that we can have 60-degree segments. But what we found was that if you make this 60-degree segments, you cannot meet the tolerances, and we had to split the 60-degree segments into two 30-degree segments, and finally they are welded and we can achieve the tolerances that we are looking for. So this actually demonstrates the need of full-scale prototypes in some cases. Coming to experimental test beds, this is a test bed at ITER India which is related to the development of cryolines. This is the test bed which is for the RF development. As I said, we have two systems. One is the dichrome based system, the other is the tetrode based system, and both of them are connected to a test rig which has a dummy load for match conditions and some kind of transmission lines to create the mismatch conditions and help us testing these tubes. So as I said, the next stage is the amplifier chain stuff. Coming to the beams, not only do we have to develop the processes, the materials, the components, we also have to develop the beams. Now, if we wait for the components to be manufactured and then we start developing the beams, it will be too late. So there's a parallel path which has been adopted here. One is to concentrate on optimizing the source and the beams and learning the art of coupling RF power. How do we tune the sources? How do we feed cesium into the source so that we get the desired power densities? How do we make the sources in India as well? Because this is one component which is made abroad. So for the beam development path, we have a test facility called Robin test bed. It's a single driver RF negative ion source. It has an extraction area of 74 centimeters square, and till date we have extracted H minus currents of 30 milliamps per centimeter square. Then we move on to because we have multiple driver sources fed by the single generator, so we moved on to the next generation source, which is the two driver source. This source is actually made in HHV in India. We have certain deviations from the requirements, but actually the idea is to see if these deviations also help us. Even with these deviations, we can make the source which works for ITER. So this is a completely homemade source, and we have started plasma operations in this. And while these things are going on, the manufacturing of this source is underway. And once this is done, then we would have learnt many technologies related to the production of the beam, to controlling the optics of the beam, to feeding cesium into the source, to realizing the desired current densities, and we would be ready for operation. We will not be starting from scratch for this source. And once we have done that, we have this Indian test facility, which is the prototype of the diagnostic neutral beam test facility. It's a 21-meter path length beam. This is one of the state-of-the-art facilities, which is from the worldwide standards. There is no facility which has beams transporting over this length, and it houses the exact components of ITER's 1:1 scale. We transport the beam over this length, which is the duct in the case of ITER. In our case also it's a duct, but a much simpler one. And finally we diagnose the beam at 21 meters using a second calorimeter. So this facility is coming up. And similarly for diagnostics, for the ECE part, the idea was to develop or establish what is the kind of attenuation that will happen if we have a 8-meter transmission length. So there's a Fourier transform spectrometer which rests in one of the labs of diagnostic labs of ITER India building, where these tests are done. Now, I have finished the technology part, but coming to quality and documentation requirements, why do we require them? The quality requirements are dictated, of course, by the French safety classification and order. We have to adhere to a lot of engineering codes. We have to comply with international standards, and we have stringent quality checks implemented at different stages of manufacturing to ensure that we get the product that we want. Coming to documentation, of course, the products are being made today by the present generation. They would be used by the future generation. So if we do not document properly the kind of prototypes we made, the kind of failures we had, the kind of improvements and quality checks we made, then when these components are actually put to use in 2035 or 2040, somebody at that point of time would have to start from scratch again. But if we have this proper documentation, and if he follows it and it is maintained correctly, then there's a lot of database which is already available, and you don't have to reinvent the wheel again. So this standard documentation, there's a ITER IDM database where all this information is being stored. We have to write the documents for each of the component that is being developed, for each process that is being developed, for all the quality checks that have been done. So we follow that quite religiously. Now this is a picture or collage of various industries which have been involved in ensuring or developing and ensuring that the deliveries are made to ITER in time. There are many more which are coming up, and many more are still showing interest, and we need to develop them to ensure that we have readiness of technology when it comes to the point where we have to build reactors for ourselves. So I like to end my talk by saying that there are many components first of their kind. They have stringent quality and performance requirements. The technologies involved are complex. The complexity increases in size, shape, safety, and quality requirements. The academia and industry have to work hand in hand and on same footing to help us develop and deliver such technological requirements. It has been a journey of development for a lot of materials and machining processes, jointing, electrical, hydraulic, cryogenic areas of engineering which had to be addressed. Several prototypes have been developed. A lot has been done, a lot has been learned, and a lot needs to be learned. A lot of facilities in the industry have come up and are coming up to help us become self-reliant. Parallel routes of development with the Indian industry have been initiated to come into the state of readiness, and number of areas of research and development are open, and we always encourage students and faculty to join hands with us to move into this mega journey of future. So with this, I end my talk. Thank you for your attention. Sorry if I have bored you. See, normal copper, if it goes beyond 200 degrees centigrade, it loses its mechanical properties. So its mechanical strength would go down. It tends to crumble. But here, this special material, even at higher temperatures, at 400 degrees centigrade of operation or whatever, its mechanical properties are almost similar to the original copper. So that's that hardness thing, so you have to go through a process of special mixing of the alloys, heat treatment cycles, forging cycles, and so on and so forth to develop that material which has this high mechanical strength even at higher temperatures. Yes, this material is developed at Non-Ferrous Technology Development Center in India in Hyderabad. Yes, ITER has accepted this material. This material has become the base for a lot of components in ITER. Yeah. No, it's done by, there are borated steel plates and ferritic steel plates, so it's done by that. It's not done by concrete. So I think I give you a flavor of why this technology is different and it takes a long time. So आगे से I think probably you will not ask me the 50 साल question.
What fraction of all these components are made directly in India, and what are the
Okay, let's say the Cryostat, as I said, is completely made in India. The whole full 30 meter by 30 meter, even the materials are made in India. Similarly, the components for the water cooling system and the cryogenic system are being made in India, except for the cryostat. But we will develop them here in the coming years. Then coming to special technologies like neutral beam, why this becomes special is for a simple reason that you have a lot of places there are copper components where you what you do is you first mill the material, you make water cooling channels in the material, and then you electro deposit 1 millimeter of copper on that. Now, this is an area of technology which is done or for the past 50 years only by a single company in the world. It has patented this technology and it is continuing with it. Tomorrow, I am sure if that man dies, ITER will be in trouble.